Tonight, our journey takes us far beyond the Earth, into the quiet darkness where the James Webb Space Telescope keeps its watch. This golden machine is more than a telescope. It is a time machine, a cosmic detective, and a window into places and ages we were never meant to see. With it, astronomers have found galaxies that appear too old to exist, stars being born behind curtains of dust, and the chemical breath of worlds circling suns light years away. But Webb is also a marvel of human engineering. A telescope so vast, it had to fold itself into a rocket, and so delicate, it hides behind a giant shield the size of a tennis court. Tonight, we'll wander through some of its greatest discoveries and engineering marvels, facts so remarkable you may not believe them at first. If these calm explorations help you unwind, consider liking and subscribing, or simply share some of your thoughts in the comments below. It helps others find their way here too, one sleepy soul at a time. Now let's begin. Webb has found galaxies that appear too old to exist. One of the very first surprises from the James Webb Space Telescope was the discovery of galaxies that seemed impossibly ancient. According to standard cosmology, galaxies should take hundreds of millions of years to build up after the Big Bang. They need time for the first stars to form, to explode in supernova, to create heavier elements, and to recycle gas into new generations. Yet, in Webb's earliest deep surveys, astronomers spotted galaxies, mature structures, existing less than 300 million years after the universe began. They appeared massive, bright, and far more developed than any model predicted. Some looked like fully formed spirals, or ellipticals, shapes that normally take billions of years to emerge. The discovery was so startling that it sent theorists scrambling to reconsider how fast galaxies can grow. Whether star formation was more efficient in the early universe, or if some unknown process accelerated their birth. Webb had, within weeks, cracked open a mystery that may force a rewrite of cosmic history. Its detectors operate just a few degrees above absolute zero. To see the faintest galaxies, Webb's detectors need to be colder than almost anything in the universe. Some of its sensors are cooled to around 40 Kelvin, just 40 degrees above absolute zero, the coldest possible temperature in nature. At this point, atoms are nearly motionless, and thermal noise is reduced to almost nothing. Without this extreme cold, the telescope's own warmth would blind it to the faint heat of distant galaxies and exoplanets. Achieving such temperatures in deep space is no simple feat. Webb uses a combination of passive cooling, hiding behind its massive sun shield, and active cooling, with a cryocooler that chills its most sensitive instruments to about 7 K, colder than liquid helium. This engineering marvel allows Webb to act like a cosmic heat camera, detecting light that has traveled across billions of years. The result is an observatory capable of picking out signals so faint they were invisible to every other telescope in history. Webb revealed Saturn's rings, glowing in infrared like never before. Saturn's rings are iconic, yet Webb's infrared eyes showed them in a completely new light. Instead of just reflecting sunlight, the icy particles that make up the rings emit their own faint heat, invisible to the human eye, but perfectly captured by Webb. This allowed astronomers to study subtle differences in particle sizes and densities across the rings. Some regions glowed brighter, showing areas rich in smaller icy grains, while darker patches hinted at clumps and collisions shaping their structure. Webb even captured faint outer rings that had only been glimpsed before, revealing just how extended Saturn's halo of debris truly is. These insights matter because the rings are not permanent. They may be remnants of shattered moons or comets slowly eroding away. By analyzing their heat and composition, Webb is helping scientists piece together how long Saturn's dazzling rings have left and what they can tell us about planetary systems across the cosmos. Engineers called its unfolding sequence 30 Days of Terror. When Webb launched, it was packed tightly inside the Ariane 5 rocket, like an impossibly complex puzzle. To operate, it had to unfold over the course of a month, step by delicate step. There were over 300 single points of failure, meaning if just one latch stuck, one motor misfired, or one cable snagged, the $10 billion telescope would be lost forever. NASA engineers referred to this process as the 30 days of terror they had to deploy the sun shield, consisting of 5 enormous, razor-thin layers, stretched out in perfect alignment. Then the secondary mirror swung into place on spindly arms. Finally, the massive primary mirror, split into 18 segments, had to unfold like the petals of a flower, and then align itself within nanometers. Each maneuver was irreversible. Watching from Earth, scientists and engineers held their breath. Against all odds, Webb's deployment went flawlessly, one of the most complicated robotic sequences ever attempted in space. Webb detected water vapor in the atmosphere of a planet hundreds of light years away. Webb isn't just for galaxies. It's also revolutionizing exoplanet science. By studying the way starlight passes through a planet's atmosphere during a transit, Webb can detect the chemical fingerprints of molecules. One of its earliest triumphs was the detection of water vapor in the skies of a hot gas giant orbiting a distant star. This doesn't mean oceans or rain, but the very fact that Webb can sense water molecules across Lakeas is extraordinary. It proves that the telescope can analyze the chemistry of alien worlds with unprecedented precision. This technique will one day be applied to smaller, Earth-like planets, where detecting water vapor could be a crucial clue in the search for life. Webb's sensitivity means we can now realistically hope to detect not just water, but carbon dioxide, methane, and maybe even biosignatures in the atmospheres of distant worlds. One side of its sun shield is hotter than boiling water, the other colder than Pluto. Webb's Favelier sun shield is one of its most vital features. Each layer is as thin as a human hair, yet together they create a thermal barrier unlike anything built before. The side facing the sun can reach temperatures of more than 100 degrees Celsius, hotter than boiling water. Just a few millimeters away, on the shaded side, the telescope chills to around minus 230 degrees Celsius, colder than the surface of Pluto. This staggering temperature difference is what allows Webb to detect faint infrared light without interference. The engineering behind the sun shield is as astonishing as the science it enables. It had to unfold perfectly in space, with each fragile layer tensioned just right. Without it, Webb would be blinded by its own heat. With it, the telescope becomes a window into the cold, ancient light of the universe. Webb captured stars in the Carina Nebula, carving caverns of dust and gas. The The Carina Nebula is a vast stellar nursery, a place where thousands of stars are being born. Webb's infrared vision pierced through clouds of gas and dust that had long hidden its most dramatic scenes. What it revealed looked like colossal cliffs and valleys. But these shapes are sculpted from cosmic material by the fierce radiation of young, massive stars. As they ignite, their energy pushes away surrounding gas, carving out enormous cavities. In the walls of these structures, new stars are still forming, their light glowing through the haze. The image is both beautiful and instructive, a snapshot of the chaotic processes that build stars and planets. Webb's view of the Carina Nebula showed us creation in action, revealing details we had never seen, and reminding us that even today, the cosmos is still very much alive with birth and change. The telescope launched on Christmas Day 2021. After decades of delays, redesigns, and rising costs, Webb finally left Earth on December the 25th, 2021. The launch was a flawless gift to science, carried aloft by an Ariane 5 rocket from French Guiana. For thousands of scientists, engineers, and astronomers who had worked on Webb, it was a day of relief and celebration. Yet the joy was tempered by the knowledge that the hardest part was still to come: deployment and alignment. The launch itself lasted only 27 minutes, but the mission would not be considered safe until a month later, when the telescope completed its unfolding sequence. Christmas 2021 became a milestone in history. The day humanity's most ambitious scientific instrument began its journey to open the universe's deepest chapters. Webb's mirror is over 6 meters wide, the largest ever launched into space. Webb's primary mirror measures 6.5 meters across, dwarfing Hubble's 2.4 meters. Its size is what allows Webb to gather enough light to see galaxies billions of light years away. But such a mirror could never fit inside a rocket in one piece. The solution was to build it from 18 hexagonal segments, each made of beryllium and coated with gold. Once in space, these segments unfolded and were aligned so precisely that together they behave like a single, flawless mirror. The tolerances are mind-boggling. Each segment had to be positioned with an accuracy of about 10 nanometers, smaller than a single virus. This enormous golden eye gives Webb the sharpness to study exoplanet atmospheres, peer through cosmic dust and sea light from the first galaxies. It is, quite literally, the most powerful mirror humanity has ever created. It observed Neptune's rings glowing in infrared for the first time. Neptune's faint rings have always been elusive. Voyager 2 glimpsed them briefly in 1989, but no telescope since had shown them clearly, until Webb. With its infrared sensitivity, Webb revealed the rings glowing with thermal light. For the first time, scientists could see details of their structure, how they vary in density, and even small features caused by the pull of Neptune's moons. The telescope also captured the planet itself with striking clarity, showing atmospheric bands and storms in a way no Earth-based telescope could match. Webb's view of Neptune was a reminder that its talents extend far beyond the distant universe. Even in our own solar system, it can reveal phenomena we've never truly seen before. Webb's first deep field image revealed thousands of galaxies in a patch of sky smaller than a grain of sand. When Webb released its very first image, the world was stunned. Astronomers pointed the telescope at a seemingly empty piece of sky, a region so small that if you held a grain of sand at arm's length, it would cover the same area. In that tiny patch, Webb revealed thousands of galaxies, some so faint their light had been stretched across nearly the entire galaxy of the universe. Many of these galaxies had never been seen before, even by Hubble. Some appeared as delicate spirals, others as glowing smudges, and some as arcs of light distorted by gravity. This single image contained more galaxies than most people will see stars in a lifetime. It was a dramatic demonstration of Webb's power. Wherever it looks, even in the quietest corners of the sky, the universe is overflowing with hidden worlds waiting to be discovered. More than 300 single points of failure had to succeed for it to work. Webb was the riskiest telescope ever built. From the moment it launched, engineers knew there were over 300 single points of failure. Each one was a part or step that, if it failed, could not be repaired or worked around. These included motors that had to fire once and only once, cables that needed to unfurl perfectly, and mirrors that had to align with unimaginable precision. Failure at any stage would have meant the end of the mission. For weeks, engineers monitored step after step, each one carrying a weight of billions of dollars and decades of effort. As Webb's sun shield stretched open and its mirrors unfolded, tension turned into awe. Against the odds, every single point of failure succeeded. This flawless sequence transformed Webb from a folded-up package inside a rocket into humanity's greatest astronomical observatory. Webb mapped storms and aurora on Jupiter in unprecedented detail. When astronomers turned Webb toward Jupiter, they weren't expecting to be able to see it. Yet, the telescope revealed the giant planet in dazzling new ways. Its infrared vision mapped massive storms raging across the atmosphere, including the Great Red Spot, which appeared as a glowing oval of heat against swirling bands of gas. Webb also captured Jupiter's aurora, bright arcs of light dancing at the poles, created by charged particles slamming into the planet's magnetic field. These aurora had been studied before, but never in such crisp detail. Webb even spotted faint rings around Jupiter and tiny moons glowing nearby. The images showed that the telescope, designed to study galaxies billions of light years away, can also reveal astonishing new features of the planets in our own solar system. Jupiter, a world we thought we knew well, suddenly looked fresh and full of secrets again. Its golden mirror is coated in real gold, only a few hundred atoms thick. The dazzling golden color of Webb's mirror is not just for show. Each of the 18 hexagonal segments is coated with an ultra-thin layer of pure gold, only about 100 nanometers thick, a fraction of the width of a human hair. This tiny amount, just 48 grams in total across the whole mirror, enhances the reflectivity of infrared light, the kind Webb was built to study. Gold doesn't tarnish in space, and it reflects infrared wavelengths more efficiently than almost any other material. The coating is applied so precisely that its thickness varies by less than a few nanometers. Without this delicate film of gold, Webb wouldn't be able to detect the faintest galaxies, the chemical fingerprints of alien worlds. The mirror's golden gleam has become an icon, not just a symbol of wealth, but of the priceless knowledge it is unmocking. Webb saw arcs of light from galaxies bent by the gravity of dark matter. In Webb's deep images, some galaxies appear stretched into arcs and curves. This strange distortion isn't a camera flaw, it's the universe itself, bending light. Massive clusters of galaxies act like cosmic lenses, their gravity so intense that it warps space and magnifies the light of galaxies behind them. Webb captured these gravitational lenses with unparalleled clarity. The arcs it sees are galaxies that would otherwise be too faint and distant to detect. By studying these distortions, astronomers can not only glimpse the most ancient galaxies, but also map the distribution of dark matter, the invisible substance making up most of the universe's mass. Every warped streak of light is a double gift, a magnified window into the distant past, and a tool to study one of the deepest mysteries of modern physics. Its detectors are so sensitive, they can spot the heat of a bumblebee on the moon. To explain Webb's incredible sensitivity, scientists often use a striking analogy. If there were a single bumblebee sitting on the surface of the moon, Webb's instruments could detect its tiny heat signature. That's because the telescope is designed to capture infrared light, essentially heat, at levels billions of times fainter than what our eyes can see. Achieving this requires extreme cold, absolute precision. In the enormous collecting area of Webb's mirror, this sensitivity is what allows the telescope to do its job. Galaxies at the edge of time, or trace the faint chemistry of exoplanet atmospheres. The bumblebee on the moon example is not just poetic exaggeration. It's a literal benchmark for Webb's power. With such capabilities, no signal in the cosmos is too faint to consider. The universe is suddenly wide open to observation. No astronaut can ever service Webb where it floats. Unlike Hubble, which orbits close enough to Earth for astronauts to repair, Webb is stationed 1.5 million kilometers away at a point called L2. This means no current spacecraft can reach it. Every part of Webb, every mirror, motor, and instrument had to be designed to work flawlessly for years without maintenance. If something fails, there is no fixing it. This raised the stakes during design and construction enormously because there was no safety net. Engineers built Webb with extreme redundancy wherever possible. But some parts, like the sun shield or the unfolding mechanisms, had no backups. Launching a 10 billion observatory with no chance of repair was a bold gamble, but one that paid off. Webb works so well that it may last for decades, but it will always be beyond human hands. Webb revealed newborn stars hidden inside the pillars of creation. The pillars of creation, made famous by Hubble, are towering columns of gas and dust in the Eagle Nebula. For decades, they appeared as shadowy silhouettes against starlight. Webb, with its infrared eyes, pierced through the clouds to reveal the stars forming inside. Hidden baby stars glowed brightly, still surrounded by the dusty cocoons of their birth. Webb also showed jets of gas streaming from young stars, carving out channels in the pillars. These features had never been seen with such clarity. The result was more than just a new image. It was a transformation. A familiar icon of astronomy became fresh again, revealing secrets it had held for billions of years. The pillars of creation are not static statues, but active nurseries, still busy with the work of building stars. It rides in orbit 1.5 million kilometers from Earth. Webb's home in space is not around Earth, but around the Sun. It orbits a special point called Lagrange Point 2, or L2, located about 1.5 million kilometers away, roughly 4 times the distance to the Moon. From there, Webb keeps Earth, the Sun, and the Moon all aligned on the same side, so its giant sun shield can block their heat and light. This orbit is stable, meaning Webb can stay in the same relative position with minimal fuel use. It also allows the telescope to observe the universe continuously, without Earth ever passing in front to block its view. Reaching L2 required a precise journey, but the location is perfect. Far enough to stay cold and quiet, yet close enough for radio contact. Webb's orbit makes it both remote and reliable, the perfect perch for exploring the cosmos. Webb has imaged galaxies distorted by gravitational lensing with unmatched clarity. Gravitational lensing isn't just a curiosity, it's a powerful scientific tool. When massive galaxy clusters bend light, they magnify distant galaxies behind them, turning Webb into an even stronger telescope than it already is. In its first year, Webb captured some of the sharpest lensing images ever taken. Background galaxies appeared stretched into arcs, sometimes even multiple copies of the same object appearing around the cluster. These natural lenses allow astronomers to study galaxies so faint and distant they would otherwise be invisible, effectively letting Webb peer deeper than even its own mirror size should allow. The clarity of Webb's lensing images also lets scientists measure the distribution of dark matter in galaxy clusters, testing our understanding of one of the universe's greatest mysteries. Every distorted galaxy in Webb's images is a cosmic gift, showing us both the past and the invisible forces shaping it. Its sun shield is the size of a tennis court and folds like origami. Webb's sun shield is one of its most extraordinary features. It's about the size of a tennis court, yet it had to fit inside the narrow fairing of a rocket. To do this, engineers designed it to fold up like an enormous piece of origami. Once in space, the 5 ultra-thin layers of the shield had to carefully unfurl, each layer stretching to precise tension. The sun shield blocks heat and light from the sun, Earth, and Moon, keeping Webb's instruments in permanent darkness and chilling them to cryogenic temperatures. Each layer is made of a material called capton, coated in reflective aluminum, thinner than a human hair, and able to withstand the harshness of space. Without this structure, Webb would quickly overheat and fail. With it, the telescope can study the faint heat of the earliest galaxies in the universe. Webb discovered galaxies forming less than 300 million years after the Big Bang. Astronomers once believed that galaxies needed at least 500 million years to take shape after the Big Bang. Webb has already overturned that assumption. In its first year of observations, it detected galaxies that existed just 200 to 300 million years after the universe began, incredibly early in cosmic history. These galaxies appear surprisingly large and bright, raising questions about how matter gathered and stars formed so quickly. Were early stars more massive and efficient than today's? Did dark matter clump faster than expected? The discovery forced cosmologists to revisit models of galactic evolution, as these ancient galaxies seem to have no right to exist so soon. Webb isn't just observing the early universe, It's rewriting the story of how the first structures emerged out of darkness. Its resolution in infrared surpasses Hubble's resolution in visible light. Hubble has long been celebrated for its sharp vision in visible light, but Webb surpasses it in the infrared. Thanks to its larger mirror and advanced detectors, Webb can capture details finer than what Hubble could achieve in shorter wavelengths. This means Webb can study faint, distant objects with unprecedented clarity. It can resolve features in galaxies billions of light years away, map the fine structure of dusty stellar nurseries, and even distinguish layers in planetary atmospheres. The achievement is remarkable. Infrared light has longer wavelengths, which usually means less sharp images. But Webb's design and size make its infrared images sharper than Hubble's visible light ones. This leap in resolution opens entirely new realms of discovery, allowing us to see cosmic structures with a level of detail never before possible. Webb captured starlight shining through curtains of gas in stellar nurseries. Stellar nurseries, vast clouds of gas and dust, where new stars are born, often appear opaque in visible light. Hubble showed them as glowing walls of gas, but Webb's infrared eyes can see through the curtains. In its images, faint starlight streams through cracks and openings in the dusty clouds, like beams of sunlight through mist. These views reveal young stars, still in their infancy, hidden inside. Some are just beginning to shine, while others are already shaping their environments with powerful winds and radiation. By watching starlight struggle through these curtains, astronomers gain a direct view into the earliest stages of stellar birth, something Hubble could only hint at. Webb's observations turn once shrouded regions into transparent windows, letting us watch creation in progress. The telescope cost nearly $10 billion to complete. Webb is the most expensive scientific instrument ever built for space. Its final cost, after decades of planning, delays, and redesigns, came in at nearly $10 billion. This immense investment was the result of extraordinary complexity, folding a 6-meter mirror into a rocket, designing a 5-layer sun shield the size of a house, and ensuring flawless operation of the system, a half-kilometers away. Critics often questioned whether such a price could be justified, but Webb's first discoveries silenced many doubts, showing that the telescope was not just successful, but revolutionary. Its cost reflects the ambition of the mission to look farther back in time than ever before, to detect the light of the first stars, and to probe the atmospheres of alien worlds. In this sense, the $10 billion bought humanity a machine that is already rewriting cosmic history. Webb revealed a planetary system still assembling from a swirling disk of gas. Young stars are often surrounded by disks of gas and dust, the raw material for building planets. Webb has observed these disks with remarkable detail, catching systems in the act of formation. In one striking case, it saw gaps and rings carved into a protoplanetary disk, evidence of planets already forming as they cleared paths in the material. These observations confirm theories about how planets emerge, but also reveal surprising complexity. The disks contain water vapor, carbon compounds, and silicates, ingredients for rocky worlds and possibly life itself. For the first time, astronomers can watch the birth of planetary systems like our own with clarity, tracing the journey from swirling gas to newborn planets. Webb is giving us front-row seats to cosmic creation stories that have been playing out for billions of years. Its first images reshaped how astronomers think about the early universe. The release of Webb's first images in July 2022 wasn't just a media event. It was a scientific turning point. Within hours of the data being made public, astronomers began identifying galaxies that seemed impossibly old, bright, and massive for their place in time. The images suggested that the early universe was far busier and more structured than expected. This forced scientists to reconsider long-standing theories about galaxy formation, star birth, and the behavior of dark matter in the young cosmos. Webb didn't just provide sharper pictures. It delivered surprises that sent shockwaves through cosmology. For many astronomers, those first images felt like the moment a door opened into a room we hadn't even known existed. Webb's orbit at L2 keeps Earth, Sun, and Moon all safely behind its shield. The placement of Webb at L2, 1.5 million kilometers away, is not just about distance. The orbit was chosen so that the Sun, Earth, and Moon are always on the same side of the telescope. This allows Webb's sun shield to block all major sources of heat and light simultaneously. With everything safely hidden behind its reflective layers, Webb can face the cold, dark universe without interference. This constant orientation means the telescope doesn't need to spin around to avoid Earth's shadow, as Hubble does. Instead, it can observe continuously, maximizing its efficiency. The design makes Webb not just powerful, but uniquely stable. A silent sentinel, with all the noisy heat of the solar system forever at its back. It has already found stars forming inside dusty clouds invisible to Hubble. Many regions of the galaxy are shrouded in dust, booking visible light. Hubble's cameras could only see the surface of these clouds, leaving the interiors a mystery. Webb, however, has peered into the densest of them and revealed stars in the earliest stages of life. Some of these infant stars are still surrounded by the disks that will form planets, while others are shooting out jets of material that carve channels in the dust. Webb has shown us stars quasars at the moment of ignition, when nuclear fusion has just begun. These are sights no human had ever seen before. The ability to detect such hidden structures makes Webb not just a telescope of distant galaxies, but also a window into the secret nurseries of our own Milky Way. Webb's mission was designed for 10 years, but could last 20 or more. When Webb launched, its mission lifetime was expected to be about 10 years, limited mainly by the fuel needed to keep it in position at L2. Thanks to the precision of its launch and flawless course corrections, Webb used far less fuel than anticipated. As a result, mission planners now estimate it could operate for 20 years or longer. This means a generation of astronomers will grow up with Webb as a constant tool, reshaping our understanding of the cosmos decade after decade. With careful management, the telescope could watch discoveries unfold not just once, but across many scientific revolutions. Webb was built to outlast expectations, and now, it seems, it will. The telescope measured carbon dioxide on an alien world for the first time. One of Webb's earliest triumphs was detecting carbon dioxide in the atmosphere of an exoplanet called WASP 39b, a hot gas giant about 700 light-years away. This may sound silly compared to the dazzling images of galaxies, but it was a game. changer. Until then, astronomers could only guess at the chemical makeup of faraway worlds. With Webb's infrared spectrograph, a clear absorption signature of carbon dioxide appeared, leaving no doubt. Why does this matter? Because carbon dioxide isn't just a random gasset. It plays a vital role in planetary climate and chemistry. On Earth, it cycles through oceans, rocks, and life itself. Spotting it so clearly on another world proved Webb could dissect exoplanet atmospheres in detail, opening the door to Sunday, detecting gases that hint at biology, like oxygen or methane. In that one observation, the telescope proved itself as not just a window into the distant past, but as a tool for probing the possibility of life elsewhere. Webb's mirror segments are aligned with nanometer precision. Webb's golden primary mirror looks like a single piece, but in reality, it is made up of 18 individual hexagonal segments. When it first unfolded, each piece pointed in a slightly different direction, scattering starlight into a mess of overlapping spots. The task for engineers was to tilt, bend, and nudge each mirror until they all acted as one flawless surface. The catch? The adjustments needed to be accurate to within tens of nanometers, tiny fractions of the width of a human hair. Imagine lining up 18 enormous golden dishes so precisely that they reflect light together as perfectly as a single giant mirror. It's an achievement that required months of careful calibration using faint stars as guides and algorithms to correct tiny imperfections. Today, those segments are so well aligned that Webb's optics are sharper than expected, delivering clarity beyond the mission's design goals. It is, in many ways, the most perfectly tuned mirror humanity has ever created. It revealed complex organic molecules in star-forming regions. Webb's instruments have peered into the dark, dusty clouds where new stars and planets are born, and what it has seen is astonishing. Signatures of complex organic molecules. In regions like the Orion Nebula, Webb has detected hydrocarbons molecules built of carbon and hydrogen that are considered the chemical building blocks of life. These molecules don't guarantee biology, but they show that the raw ingredients for life, as we know it, are widespread in space, forming naturally in the chaos of stellar nurseries. Even more striking is that Webb can map where these molecules exist, tracing how radiation from newborn stars sculpts the chemistry around them. For decades, scientists debated whether such fragile compounds could survive in such harsh environments. Webb has now confirmed they do, painting a picture of the cosmos as chemically rich and fertile. Every time its detectors spot these molecules, the case for life being a universal phenomenon grows stronger. Webb peered into disks of dust where new planets are being born. One of Webb's greatest strengths is its ability to see through the thick veils of dust that once hid the earliest stages of planet formation. Around young stars, vast disks of dust and gas swirl, slowly collapsing into one another. Worlds. Webb has captured these disks in extraordinary detail, revealing gaps and rings carved by newborn planets still coalescing from rubble. For the first time, astronomers can watch planetary systems in their infancy worlds, assembling before our eyes. Some disks show evidence of turbulence, with giant planets already shaping their orbits, while others appear like flattened pancakes of dust, just beginning their journey toward building rocky planets. These observations give us direct insight into how our own solar system must have formed billions of years ago. What was once pure theory has become a visible reality. The birth of planets, frozen in light and dust, caught by Webb's gaze. Its instruments can analyze the chemical fingerprints of distant atmospheres. When light passes through a planet's atmosphere, some wavelengths are absorbed by gases, leaving behind a unique fingerprint. Webb's spectrographs are designed to capture these patterns in exquisite detail, letting astronomers identify the gases present on alien worlds. Already, Webb has detected water vapor, carbon dioxide, sodium, and even possible hazes and clouds on exoplanets hundreds of light years away. These techniques are so sensitive that they can reveal not just what gases are present, but in what quantities and even at what altitudes in the atmosphere. This is how, one day, we might identify biosignatures, chemical clues that suggest life. It's astonishing to think a telescope 1.5 million kilometers from Earth can look at the faint light of a star, separate out the glow of a tiny planet, passing in front and read its chemistry like a barcode. That's not just astronomy. It's planetary forensics on a cosmic scale. Webb has begun mapping the hidden scaffolding of dark matter. Dark matter is one of the greatest mysteries in physics. We can't see it, but its gravity shapes the universe, pulling galaxies into clusters and sculpting vast cosmic webs. Has already started to trace this invisible structure using a phenomenon called gravitational lensing. When light from distant galaxies passes by a massive cluster, it bends and distorts, creating arcs and stretched shapes. By analyzing these distortions in incredible detail, Webb reveals how much unseen mass must be there and where. In doing so, it provides a map of dark matter, a ghostly scaffolding that holds the visible universe together. The sharper Webb's vision, the more precise these maps become, helping scientists probe how dark matter behaves and whether it matches predictions of physics. With every arc of bent starlight Webb records, we get closer to understanding a force that makes up most of the matter in the cosmos, yet remains entirely invisible. The telescope unfolded in space like a giant golden flower. Webb was far too large to fit inside the rocket fully assembled. Instead, it was launched folded up, like a colossal piece of origami. Once it reached space, it had to perform one of the most intricate deployment sequences ever attempted. Over the course of weeks, its solar panels extended, its sun shield unfurled in layers, and its mirrors swung into place. Each step carried risk. Over 300 individual mechanisms had to work perfectly, and if even one failed, the mission could be lost. Engineers called it 30 days of terror. Against all odds, everything worked flawlessly. Piece by piece, Webb broomed in space, transforming from a compact payload into the most powerful space observatory ever built. Watching this unfold was like witnessing a mechanical flower open in the void, delicate, precise, and utterly breathtaking. Humanity had never before attempted something so complex, so far from home. And yet, Webb now floats complete. Webb captured colliding galaxies in the act of merging. Galaxies are not static islands of stars. They move, collide, and merge in slow motion cosmic dances. Webb has already captured spectacular images of galaxies crashing together, their shapes warped and twisted by gravity. In these collisions, clouds of gas are compressed, triggering furious bursts of star formation, while central black holes gorge on the chaos. Webb's infrared eyes can peer into the dusty hearts of these mergers, places Hubble could barely penetrate, and reveal the processes reshaping galaxies from within. These observations are more than just beautiful. They help astronomers understand how galaxies like our Milky Way grew over billions of years, often through violent unions with their neighbors. When we look at Webb's pictures of merging galaxies, we are also looking into our own past, for the Milky Way itself was built from countless collisions. In Webb's vision, we can see cosmic evolution in motion. Its first data forced astronomers to rewrite of galaxy growth. One of Webb's most surprising discoveries came quickly. Galaxies in the early universe were brighter, bigger, and more mature than theory predicted. Before Webb, astronomers assumed it took billions of years for large, organized galaxies to form. Yet Webb's deep field images revealed massive galaxies already thriving less than 1 billion years after the Big Bang. This contradicted established models of how fast stars could form and how matter could clump together. Some of these galaxies even looked like giant ellipticals, the type we thought should only appear much later in cosmic history. Suddenly, textbooks and simulations were out of date. Astronomers are now racing to adjust theories, asking whether physics is missing something, or if galaxy formation is simply more efficient than we imagined. Webb didn't just add details, it reshaped our picture of the universe's timeline. Its data forced us to admit the cosmos grew up much faster than we thought. Webb revealed Jupiter's faint, thin rings in crisp detail. Hubble once glimpsed Jupiter's faint rings, but only barely. With Webb, those delicate halos of dust shine clearly, wrapping the gas giant in ghostly bands. Unlike Saturn's broad, icy rings, Jupiter's are thin and dark, made mostly of dust from shattered moons and meteoroid impacts. Webb captured them alongside glowing auroras at Jupiter's poles and swirls of storm clouds rolling across its atmosphere. For the first time, scientists can study these fragile rings in detail, how they form, how they interact with Jupiter's powerful magnetic field, and how small moons contribute to them. To most of us, Jupiter is already familiar with its great red spot and striped atmosphere. But Webb reminds us that even in our own solar system, there are features we barely understand. Its crisp images turned a once ghostly hint of rings into something tangible, beautiful, and mysterious, showing that even our planetary neighbors still hold surprises. Webb can detect heat fainter than the glow of a candle millions of kilometers away. The James Webb Space Telescope was built to see the faintest whispers of light. Its detectors are so sensitive that if you placed a single candle on the surface of the moon, Webb could pick out its heat. That level of precision is required because the galaxies Webb studies are unimaginably faint. Their light has traveled for more than 13 billion years, stretching into infrared wavelengths as the universe expands. Detecting them is like listening for the rustle of a single leaf in the middle of a hurricane. The telescope must remain shielded from even the tiniest sources of heat, including itself, so its detectors are cooled to just a few degrees above absolute zero. Without this, the faintest galaxies, exoplanets, and star-forming regions would be drowned out by background noise. Webb's extreme sensitivity means it can study details in the universe invisible to every other telescope ever built. Webb showed us stars wrapped in cocoons of dust that will one day form planets. The process of star and planet formation has always been shrouded in mystery, hidden inside thick clouds of gas and dust. Hubble could only catch glimpses of these regions of mystery, but Webb's infrared vision cuts straight through the veils. One of the telescope's most striking achievements has been imaging protostars still wrapped in their dusty cocoons. These are stars in their infancy, glowing faintly as gravity compresses their cores. Around many of them, Webb has seen disks of swirling dust, the raw material that will eventually clump together to form planets, moons, and asteroids. It is essentially looking at the earliest blueprints of solar systems. These cocoons show us snapshots of our own sun's childhood, more than 4.5 billion years ago, when Earth itself was still just dust swirling in a nebula. The project took over 30 years from idea to launch. The idea for Webb began in the early 1990s, even before Hubble was fully operational. Astronomers knew they would one day need a telescope capable of seeing further back in time, beyond what Hubble could reach. Designing it, however, proved one of the most ambitious projects in the history of science. The telescope's segmented mirror, massive sun shield, and foldable design all had to be invented essentially from scratch. Budget overruns, delays, and technical setbacks pushed its timeline further and further, leading some to wonder if it would ever fly at all. By the time Webb launched in December 2021, more than 3 decades of work had gone into it. Thousands of engineers, scientists, and technicians had contributed, many devoting their entire careers to the project. Its success represents not just a triumph of technology, but of human persistence and patience. Webb revealed its shining with surprising brightness in the early universe. One of Webb's first shocks to astronomers came when it pointed its mirror toward the early universe. The galaxies it found were far brighter than theory predicted. According to models, galaxies just a few 100 million years after the Big Bang should have been faint, fragile, and struggling to assemble their first stars. Instead, Webb showed massive, luminous galaxies shining as if they had already lived through billions of years of growth. This discovery shook cosmology because it suggested galaxies might form much faster and more efficiently than previously thought. Either the first stars burned far hotter than expected, or the physics of galaxy formation needs to be rewritten. The brightness of these galaxies remains one of Webb's most puzzling findings, a sign that even now, with our most powerful telescope, the universe is still full of surprises. It has already confirmed dozens of new exoplanets. While Webb's primary mission is to peer deep into the past, it is also rewriting our understanding of planetary systems around other stars. The telescope has already confirmed the existence of dozens of exoplanets, some through direct imaging and others by analyzing the light of their host stars as the planets pass in front. But Webb goes beyond simple detection. Its instruments can measure the atmospheres of these worlds, spotting key molecules like water vapor, methane, and carbon dioxide. In doing so, Webb is opening the door to a new era of comparative planetology, studying alien worlds in as much detail as we study planets in our own solar system. Each discovery adds to the mystery. Catalog of planets, ranging from gas giants larger than Jupiter to rocky Earth-sized worlds. Some may even orbit within their star's habitable zone, where liquid water could exist. Webb's instruments can study up to 100 galaxies at once. The near-infrared spectrograph, NIRS-spec, one of Webb's key instruments, is designed for efficiency. Using a system of tiny shutters that open and close individually, it can observe the spectra of up to 100 different galaxies at the same time. This is revolutionary. Previous instruments could only study one or a handful of targets at once, meaning surveys took years. Webb can now map out hundreds of galaxies in a single session, gathering details about their composition, distance, and motion. Each spectrum carries the fingerprints of the elements inside those galaxies: hydrogen, helium, carbon, oxygen, and heavier elements forged in stars. By comparing many galaxies at once, astronomers can see how the universe evolved as a whole, not just through isolated snapshots. It's like being able to read not one diary, but 100, each written at a different time in cosmic history. Webb revealed the dusty remains of a star that exploded thousands of years ago. When a massive star ends its life, it erupts in a supernova, scattering its outer layers into space. Webb has captured these remnants in unprecedented detail. In the Southern Ring Nebula, the telescope revealed delicate shells of dust and gas cast off by a dying star. These dusty remains are not just beautiful, they are essential for the cycle of cosmic life. The material ejected in supernova eventually enriches interstellar space, seeding it with heavy elements like carbon, oxygen, and iron. Without those explosions, planets like Earth and the life that depends on them could never exist. Webb's images show the intricate structures of these stellar graveyards, tracing the shock waves, knots, and filaments left behind. By studying them, scientists learn how matter is recycled across billions of years, turning death into the foundation for new worlds. Webb detected sand, like grains in alien atmospheres. One of Webb's most intriguing discoveries has been evidence of silicate particles, grains of rock, essentially sand, suspended in the atmospheres of distant exoplanets. This was something astronomers did not expect to see. These grains are likely formed in high-altitude clouds, where temperatures and pressures allow small particles of minerals to condense. On Earth, we associate sand with beaches and deserts, but on giant exoplanets, it may exist in clouds that whip around the planet at thousands of kilometers per hour. The presence of silicates has huge implications. It tells us about the chemistry of alien skies, the dynamics of their weather systems, and the diversity of planetary atmospheres. It also suggests that the building blocks of rocky worlds may be widespread, drifting not just on solid surfaces, but even floating in the air of alien planets. Its solar panels must remain lit at all times to power the mission. Webb floats far from Earth, 1.5 miles away at a stable point called L2. There, it cannot rely on batteries alone. Its large solar panel provides constant power. The catch is that the panel must always face the sun. This requirement dictates how the telescope is oriented, how it maneuvers, and how long it can look at any given target. If the panel ever stopped receiving sunlight, the mission could be in jeopardy. At the same time, the telescope's delicate instruments must remain in deep cold, shielded from that same sunlight by its massive sun shield. Balancing these two needs, warmth for electricity, cold for observation, is one of the elegant engineering feats of Webb's design. Its constant orientation toward the sun ensures that it can continue observing for years to come. Webb captured the Southern Ring Nebula in unprecedented detail. The Southern Ring Nebula is one of the sky's great jewels, a glowing oval of gas and dust cast off by a dying star. Hubble imaged it decades ago, but Webb's view revealed details that had never been seen before. With its infrared eyes, Webb pierced through the gas to uncover a hidden binary system, two stars, not one, at its center. The faint companion star was the true sculptor of the nebula, shedding its outer layers in waves. The telescope also showed delicate arcs, ripples, and complex knots of material spreading out into space. These structures trace the dying breaths of a star not unlike our sun, offering a preview of what may one day happen in our own solar system. Webb's view turned to the moon. What was once a faint blur into a masterpiece of cosmic detail. Webb saw comets shedding ancient dust left over from the solar system's birth. Comets are time capsules. Most formed more than 4.5 billion years ago, when the solar system itself was assembling from gas and dust. Webb has already observed comets releasing fine grains of ancient material into space, dust that hasn't been touched since the solar system's earliest days. In visible light, comets look like fuzzy snowballs with glowing tails. But in Webb's infrared vision, astronomers can see the actual composition of what they're shedding. Silicates, carbon compounds, and even the raw pound bear, building blocks of planets. Studying this dust is like holding a preserved sample from before Earth was fully formed. Every particle carries clues about the chemistry that went into making oceans, atmospheres, and maybe even life itself. With Webb, astronomers can track how these primordial crumbs still wander through space, unchanged since the beginning, quietly reminding us where we came from. Webb's golden mirror has already become an icon of space exploration. Few scientific instruments have a silhouette as instantly recognizable as Webb's. Its 18 hexagonal segments form a honeycomb of shining gold, 6.5 meters across. The design isn't just functional, it's become a symbol of exploration itself. Engineers coated the mirror with just 48 grams of real gold, thin enough to be invisible to the naked eye, but perfect for reflecting infrared light. When Webb was finally unfolded in space, the golden mirror became a kind of cosmic mirror, instantly associated with humanity's search for origins. It appears in documentaries, posters, and even children's books as the face of modern astronomy. Like the rings of Saturn or the spiral of the Milky Way, Webb's mirror has crossed into the realm of icons, proof that engineering and science can produce not only knowledge, but also beauty that resonates with everyone there. Who looks at it? It revealed galaxies colliding when the universe was still young. Webb was built to look back in time. And one of its most startling findings has been images of galaxies in the act of merging when the universe was only a fraction of its current age. Collisions are cosmic engines. When two galaxies slam together, their gravity twists stars into arcs, compresses clouds of gas, and ignites furious waves of new star formation. Astronomers once assumed galaxy mergers were rarer in the early universe, but Webb is showing that they happened often, even surprisingly early. This matters because collisions shape the growth of galaxies like our own Milky Way. By catching them in the act billions of years ago, Webb gives scientists a front-row seat to the chaotic adolescence of the cosmos. Every warped spiral and tidal tale Webb reveals is like a crime scene photograph from the ancient universe, frozen in light that took billions of years to reach us. Webb measured the temperature of icy moons in the outer solar system. Webb isn't only a time machine for distant galaxies, it can also turn its golden eye toward our own backyard. Astronomers have already used it to measure the surface temperatures of icy moons orbiting giant planets in the outer solar system. These include moons suspected of harboring underground oceans like Europa and Enceladus, where liquid water may still slosh beneath a crust of ice. By observing them in infrared, Webb can track how sunlight warms their frozen surfaces or how heat escapes from cracks and geysers. Subtle temperature patterns could even hint at where liquid water lies closer to the surface. For the search for life, this is critical. Knowing where warmth and chemistry exist today helps narrow down the targets for future missions, but may one day probe these worlds directly. Webb is effectively scouting ahead, offering the first thermal maps of these enigmatic moons. Its discoveries are rewriting astronomy textbooks in real time. Normally, the process of rewriting science textbooks takes decades of gradual progress. With Webb, it began almost immediately. Within months of its first images, astronomers were already calling into question long-standing models of galaxy formation, stellar birth, and the timeline of the early universe. Galaxies Webb found seemed too massive, too bright, too soon, forcing scientists to revisit equations that had seemed settled. Star-forming regions turned out to be more dynamic and chaotic than once thought, packed with details invisible to Hubble. Even familiar planets in our own solar system, like Jupiter, revealed new layers of complexity under Webb's gaze. This torrent of discovery is unusual in its speed. Students learning astronomy today may find that their textbooks are outdated within a year. Webb isn't just asking details, it's forcing a rethinking of cosmic history itself, making astronomy one of the most rapidly shifting sciences of the moment. Webb can separate the light of a planet from the glare of its star. For decades, one of astronomy's greatest challenges has been isolating the faint light of an exoplanet from the overwhelming blaze of its parent star. The planet might be 1 billion times dimmer than its sun, making it vanish into the glare. Webb, however, was designed with instruments capable of teasing those faint signals apart. By carefully blocking and filtering starlight, Webb can detect the spectral fingerprint of a planet's atmosphere. Gases like carbon dioxide, methane, and water vapor. This ability transforms exoplanet science from "we found it" to "we know what it's made of." For the first time, astronomers can begin identifying which planets are rocky, which are gas giants, and which might even be capable of supporting life. Webb is in essence turning pinpricks of light into places, separating worlds from their stars across light years of space. The mission is a partnership between NASA, ESA, and the Canadian Space Agency. Though NASA often gets the spotlight, Webb is truly an international endeavor. The European Space Agency, ESA, contributed major instruments, launch services, and technical expertise, while the Canadian Space Agency's CSA provided the fine guidance sensor that allows Webb to aim with exquisite precision. Without Canada's contribution, Webb wouldn't be able to hold steady on distant targets long enough to capture its ultra-sharp images. The European Ariane 5 rocket carried Webb into space, one of the most precise launches in history. This collaboration represents a global effort to answer universal questions. How did galaxies form? Where do stars come from? Could life exist elsewhere by pooling resources, expertise, and funding? These agencies created a telescope no single nation could have managed alone. Webb stands as a reminder that science thrives when humanity works together on goals larger than any border or flag. Webb's images of the Tarantula Nebula showed thousands of stars never seen before. The Tarantula Nebula, located about 160,000 light-years away, is the most active star-forming region in our galactic neighborhood. Earlier telescopes had revealed it as a glowing cloud of gas, but Webb pierced through the dust to reveal something extraordinary. Thousands of young stars, some just beginning to shine, others still wrapped in cocoons of gas. Many of these stars were invisible to Hubble, hidden in wavelengths it couldn't detect. Webb's infrared vision unveiled an entire population of stars in the making, turning what looked like a luminous fog into a bustling nursery. Astronomers can now trace how winds from massive newborn stars carve shapes into the surrounding dust, setting the stage for the next generation of stellar birth. For anyone who has ever wondered how the night sky fills with stars, Webb's Tarantula image is as close as we've ever come to seeing the process unfold. It discovered faint dwarf galaxies orbiting massive galaxies. Not all galaxies are titanic spirals or giants packed with billions of stars. Many are faint dwarfs, small collections of stars that orbit larger galaxies like satellites. These dwarfs may hold some of the deepest secrets of cosmic history because they preserve conditions close to the early universe. Webb has already detected populations of such galaxies clustered around massive ones, faint enough that previous telescopes missed them entirely. Understanding these tiny galaxies is critical. They may have been the building blocks that merged to form galaxies like the Milky Way. By studying their structure, composition, and star formation, astronomers can piece together the recipe for galactic evolution. In a sense, dwarf galaxies are fossils, remnants of a time when the cosmos was assembling itself. Thanks to Webb's unprecedented sensitivity, the faintest of these cosmic fossils are finally being brought into the light. Webb's detectors must stay colder than -200 degrees Celsius. Webb works in infrared, and that means its instruments must remain unimaginably cold to avoid being blinded by their own heat. The detectors operate at temperatures colder than -200 degrees Celsius, just a few dozen degrees above absolute zero. Keeping the telescope this cold is an engineering marvel. Its enormous sun shield blocks the heat of the sun, earth, and moon, while special radiators bleed away any residual warmth. In addition, some instruments are chilled further with active cryocoolers, ensuring they remain sensitive to the faintest whispers of light. If Webb were even slightly warmer, The heat would overwhelm the delicate signals from distant galaxies. Instead, its detectors sit in perpetual deep freeze, allowing the telescope to function as a true cosmic time machine. Cold, in this case, is not just a feature, it's the key to everything Webb can do. Webb has spotted tiny asteroids invisible to other observatories. One of Webb's surprises came not from the distant cosmos, but from our own solar system. While calibrating its instruments, astronomers noticed faint, moving points of light passing across the field of view. These turned out to be small asteroids, some less than a kilometer wide, orbiting quietly in the asteroid belt between Mars and Jupiter. Many of them were too dim for previous telescopes to detect, yet Webb picked them up effortlessly in its infrared vision. These discoveries highlight how Webb is not only rewriting what we know about the early universe, but also improving our understanding of our own celestial neighborhood. Finding such small asteroids matters because they are leftover building blocks from the solar system's birth. By studying them, astronomers can learn about the raw materials that once formed planets, moons, and perhaps even the ingredients of life itself. Webb revealed arcs of light stretched across the sky by gravity itself. Among Webb's most breathtaking images are faint, delicate arcs that curve around clusters of galaxies. These arcs are not actual objects, but the stretched light of galaxies lying far behind the cluster. The effect, called gravitational lensing, happens because the immense gravity of a galaxy cluster bends space-time, warping the path of light, like glass bending an image. Hubble captured such arcs before, but Webb's infrared sharpness revealed them in unprecedented clarity. Thin threads and multiple mirrored copies of galaxies billions of light years away. Each arc is like a magnifying glass view into the deep past, showing galaxies too faint to be seen otherwise. This natural cosmic lensing allows Webb to probe even further back in time than its own optics would allow, turning gravity itself into a telescope and uncovering galaxies formed only a few 100 million years after the Big Bang. Its images of the Carina Nebula look like mountains of dust lit from within. Webb turned its gaze toward the Carina Nebula, a massive star-forming region about 7,500 light-years away, and produced one of the most iconic images in modern astronomy. What Webb saw looked like jagged mountain ranges glowing from within, but these are not mountains. They are towering walls of gas and dust, sculpted by the intense radiation and stellar winds of newborn stars. Webb's infrared view pierced through the dusty shrouds to reveal stars in the act of formation, shining like embers embedded in a smoky veil. Some of these stars are only a few 100,000 years old, infants on cosmic timescales. The detail Webb revealed has given astronomers new insights into how stars ignite and carve cavities in their birth clouds. For the public, the image captured the imagination, a landscape both alien and oddly familiar, as though nature itself were painting with starlight. Webb may uncover the universe's very first black hole. One of the great mysteries in astronomy is how the earliest black holes formed. Supermassive black holes, containing millions or even billions of times the mass of our sun, already existed when the universe was less than 1 billion years old. How they grew so quickly remains unknown. Webb is the best tool humanity has ever had to search for their origins. By peering into the faintest, most distant galaxies, Webb can detect the telltale signatures of black holes feeding on matter, hot gas swirling in, glowing brightly in infrared light. These seeds of the first black holes may have formed directly from collapsing clouds of gas, or perhaps from the explosions of the very first stars. If Webb can distinguish between these scenarios, it will finally answer how cosmic giants emerged so early, shaping galaxies and influencing the structure of the universe itself. Its instruments can detect methane and water vapor across light years. Webb is not just a telescope for distant galaxies. It is also a laboratory for studying alien worlds. By observing a planet as it passes in front of its star, Webb can measure how starlight filters through the planet's atmosphere. Different molecules absorb different wavelengths of light, leaving distinct fingerprints. Already, Webb has detected water vapor, carbon dioxide, and methane in the atmospheres of planets many light years away. These findings are more than scientific curiosities. They are stepping stones toward identifying potentially habitable worlds. Water is essential for life as we know it, while methane could signal geological or even biological activity. Webb's precision allows scientists to study the atmospheres of smaller, rocky exoplanets, inching closer to the long-sought dream of finding Earth, like conditions beyond our solar system. Each detection brings us closer to answering whether we are alone in the cosmos. Webb's mirror is made of beryllium, chosen to withstand extreme cold. Unlike ordinary glass mirrors, Webb's massive 6.5-meter mirror is crafted from beryllium, a rare, lightweight metal. Beryllium was chosen because it remains incredibly stable at cryogenic temperatures. At Webb's operating environment, colder than -200 degrees Celsius, most materials would shrink, warp, or crack. But beryllium holds its shape, ensuring the mirror maintains perfect precision. Each of Webb's 18 hexagonal segments was painstakingly polished, then coated with a microscopically thin layer of gold to optimize reflection of infrared light. The engineering challenge was immense. Not only must the mirror survive launch vibrations, but it must also expand, unfold, and align itself with nanometer accuracy in the cold of space. The choice of beryllium allowed engineers to build a mirror both strong and feather-light, capable of capturing photons that have traveled across the entire history of the universe. It revealed star clusters that may be the seeds of giant galaxies. Webb has revealed dense knops of stars in the earliest galaxies, clusters that may represent the building blocks of the massive galaxies we see today. These star clusters appear as bright, compact regions embedded within young galaxies, glowing in Webb's infrared images. Some astronomers think they could be the precursors to today's globular clusters, while others suggest they might merge together to form the central bulges of future galaxies. What makes these discoveries so remarkable is their timing. Webb sees them only a few 100 million years after the Big Bang, suggesting that galaxy assembly began far sooner than theory predicted. Each cluster contains tens of thousands of stars, packed tightly together, burning hot and fast. By studying them, Webb is showing us the scaffolding of cosmic evolution, how the grand spirals and ellipticals of today began as tiny starry seeds in the young universe. Webb found massive galaxies existing shockingly early in cosmic history, perhaps Webb's most startling discovery so far. is the detection of enormous galaxies that should not exist so soon after the Big Bang. In its earliest deep field images, astronomers spotted galaxies with masses rivaling or exceeding that of the Milky Way. Yet they were seen as they existed only 300 to 500 million years after the universe began. According to previous models, galaxies of that size should have taken billions of years to grow. The discovery has forced scientists to revisit their assumptions about how fast stars could form and how efficiently matter could clump together in the young universe. Some astronomers have even called these galaxies universe breakers because they challenge established cosmology. Whether these are truly massive galaxies or something even stranger, Webb has already cracked open one of the deepest puzzles of cosmic history. Its images of Jupiter show aurora glowing brighter than expected. While Webb is famous for exploring the distant universe, it has also turned its gaze much closer to home, producing some of the sharpest images ever taken of Jupiter. In infrared light, Jupiter's aurorae, vast curtains of charged particles colliding with the atmosphere, glow brilliantly around the poles. These aurorae are far brighter and more dynamic than scientists anticipated. Powered by Jupiter's strong magnetic field and interactions with its volcanic moon Io, Webb also revealed the planet's thin, faint rings, delicate as spiderwebs, and intricate cloud layers banded across its massive atmosphere. These observations aren't just visually stunning. They help planetary scientists understand the complex weather systems and energy flows of the gas giant. The images proved that Webb is not only a machine for peering billions of light years away, but also a powerful observatory for exploring the giant planets of our own solar system. Webb has glimpsed violent storms raging on distant alien worlds. Webb's ability to study exoplanet atmospheres is so precise that it can detect not just composition, but weather. On some gas giants orbiting close to their stars, Webb has seen evidence of enormous storms, winds whipping around the planet at thousands of kilometers per hour, and clouds made of exotic materials like silicates. These hot Jupiters, with temperatures hotter than molten lava, show night and day sides with extreme contrasts, one glowing like a furnace, the other shrouded in relative darkness. By observing the way infrared light shifts as these planets orbit, Webb can map their atmospheres and track heat circulation. For the first time, astronomers are watching alien weather unfold light years away, with storms larger than Earth itself churning in alien skies. These discoveries bring a strange kind of familiarity: storms, clouds, winds, but in worlds unlike anything we could have imagined. Its fuel efficiency has already far exceeded expectations. When Webb launched, one of the biggest uncertainties was how much fuel would remain after it reached its final orbit. The spacecraft must constantly make small corrections to keep itself balanced at the L2 point, 1.5 million kilometers from Earth. Engineers expected this fuel to last around 10 years, setting the telescope's projected mission length. But thanks to the remarkable precision of the Ariane 5 rocket and Webb's flawless deployment, the telescope used far less fuel than planned. In fact, the remaining fuel is enough to potentially extend the mission 20 years or more. This bonus longevity means that Webb won't just be a short-lived window into the cosmos. It could become a decade-spanning observatory, continually rewriting our understanding of galaxies, stars, and exoplanets. A mission that was expected to last a decade may now span an entire generation of astronomers. Webb revealed light from galaxies older than 10 times the age of Earth. Earth is about 4.5 billion years old. But Webb has already detected light that set out when the universe itself was less than 1 billion years old. That means Webb is capturing galaxies whose light has traveled more than 10 times longer our planet has even existed. In some cases, these galaxies are seen as they were over 13 billion years ago, during the first few percent of cosmic history. Their faint glow is stretched into infrared by the expansion of the universe, invisible to telescopes like Hubble, but perfectly suited for Webb's detectors. These galaxies are not only ancient, they are also surprisingly bright, packed with stars that formed earlier than expected. By studying them, Webb is directly observing how the very first cosmic structures assembled, providing a bridge between the birth of the universe and the galaxies we see today. It has already begun measuring how fast the first galaxies grew. One of Webb's most important contributions is helping astronomers understand the growth rate of early galaxies. By studying their brightness and mass at different epochs, Webb can estimate how quickly stars formed and matter accumulated. The early data shocked scientists. Galaxies appeared to be forming stars at much faster rates than predicted by simulations. Some of these galaxies seem to double their stellar populations in just a few tens of millions of years, a blink of an eye in cosmic terms. These results suggest that the early universe may have been far more efficient at turning gas into stars than previously believed. If this trend holds, theories of galaxy formation may need to be rewritten. Webb is, in effect, showing us the first growth charts of the cosmos, tracking how infant galaxies grew up into the grand spirals and ellipticals that dominate today's universe. Webb's first exoplanet spectrum confirmed the presence of clouds and hazes. When Webb observed its first exoplanet, a gas giant called WASP 96b, it delivered something revolutionary, a detailed spectrum of the planet's atmosphere. The data revealed clear signs of water vapor, but also something unexpected: clouds and hazes. Earlier models had predicted a clear, cloud-free atmosphere. But Webb's infrared precision showed a far more complex reality. These hazes could be made of exotic materials, and they scatter light in ways that make the planet's spectrum less transparent. This single observation demonstrated the power of Webb to study worlds beyond our solar system in unprecedented detail. It also hinted at just how diverse exoplanet atmospheres can be. For scientists searching for habitable worlds, the finding was a milestone. Proof that Webb can read the skies of alien planets, opening the door to eventually detecting conditions favorable for life. It discovered chemical fingerprints in the atmospheres of giant planets. Beyond WASP 96b, Webb has turned its instruments on other gas giants and hot Jupiters, unveiling their chemical makeup with astonishing clarity. In some, it found sodium and potassium in others, carbon dioxide and methane. These chemical fingerprints tell scientists about the processes shaping planetary atmospheres and the dynamics of heat, winds, and cloud formation. What's most remarkable is how far away these planets are. Some orbit stars hundreds of light years distant, yet Webb can detect individual molecules in their skies. These discoveries are more than catalogs of chemicals. They are a demonstration that Webb is the first telescope capable of comparative exoplanetology, studying not just one or two worlds, but whole populations of planets side by side. With each atmosphere analyzed, Webb builds a library that will eventually help scientists determine which worlds are lifeless and which might hold the potential for something more. Webb revealed intricate detail in planetary nebulae where stars end their lives. When stars like our Sun near the end of their lives, they shed their outer layers in beautiful, glowing shells of gas called planetary nebulae. Webb has observed these in stunning detail, including the famous Southern Ring Nebula. Its infrared eyes uncovered structures hidden from optical telescopes, delicate filaments, overlapping shells, and even the dim companion star responsible for shaping the nebula. Webb showed how dying stars enrich their surroundings with carbon, oxygen, and other elements, the very ingredients that later form planets and life. These images are not just strikingly beautiful, they are scientifically essential. They reveal how matter cycles through the galaxy, with each generation of stars seeding the raw materials for the next. In this sense, Webb's views of planetary nebulae tell a story of renewal, where stellar death becomes the foundation for future creation. Its detectors can sense just a few photons per second from distant stars. Webb's sensitivity is so extreme that it can detect just a trickle of photons arriving from objects billions of light years away. Its instruments were designed to operate in the infrared, where photons are fewer and harder to catch than visible light. Each detector is cooled to only a few degrees above absolute zero, eliminating nearly all background noise. This means that even the faintest signals, just a handful of photons per second, can be measured. To put that into perspective, if you lit a candle on the surface of the moon, Webb's instruments would be able to detect its glow. This staggering sensitivity is what makes Webb capable of peering into the universe's earliest moments. Every faint photon it captures carries information from a time and place otherwise beyond human reach, adding to a cosmic mosaic that spans the history of everything. Webb is both a time machine and a window into alien worlds. Few instruments in human history have had such a dual purpose. Webb simultaneously serves as a cosmic time machine, peering back more than 13 billion years, and as a powerful tool for probing the diversity of exoplanets orbiting stars close to home. No other telescope has combined these two capabilities with such strength. On one hand, Webb is showing us galaxies assembling in the early universe, revealing how cosmic structures first emerged. On the other, it is detecting water, methane, and hazes in the atmospheres of planets that could, in time, provide evidence for life. This duality is part of what makes Webb unique. It doesn't just study distant galaxies or just study nearby planets. It bridges the largest and smallest scales in astronomy, connecting the evolution of the cosmos with the question of whether any of those worlds might host life. It revealed star clusters forming in chains along cosmic filaments. Webb has imaged young galaxies where stars are not scattered randomly, but instead align along long thread-like structures. These filaments are the scaffolding of the cosmic web, vast networks of dark matter and gas that shaped where galaxies formed. Within them, Webb has spotted clusters of stars forming like beads on a string, each cluster destined to grow into part of a larger galaxy. This discovery provides direct evidence of how structure in the universe grows from the bottom up, starting with tiny knots of matter that link together to form cosmic giants. Observing these filaments is like seeing the universe's hidden architecture revealed. Where Hubble showed us galaxies as isolated objects, Webb is now showing us how those galaxies connect, how they grew, and how their stars assembled along invisible rivers of matter that stretch across the cosmos. The telescope has already forced scientists to rethink how galaxies form. Perhaps the most profound outcome of Webb's first year is that its discoveries have upended long-standing theories of galaxy formation. Galaxies were expected to form slowly, gradually building up their stars over billions of years. Instead, Webb has revealed galaxies that are massive, bright, and mature, shockingly early in cosmic history. Star formation appears to have been far more intense and efficient than models predicted. In some cases, galaxies look more like fully developed spirals and ellipticals just a few 100 million years after the Big Bang. These findings challenge not only galaxy formation theories, but also the underlying cosmological assumptions about how matter clumped together in the early universe. In this sense, Webb is not just answering questions, it is creating entirely new ones, forcing scientists to go back to the drawing board and rethink the story of how galaxies came to be. Webb observed Mars's atmosphere in surprising detail. Mars has been studied by dozens of spacecraft, yet Webb brought something new to the table. Using its infrared instruments, Webb measured the thin Martian atmosphere in exquisite detail, detecting carbon dioxide, water vapor, and traces of other gases. What surprised scientists was how clearly Webb could track changes in temperature and dust content across the planet's surface, even from its distant vantage point at L2. Unlike orbiters around Mars, Webb doesn't just take local readings, it captures the global state of the atmosphere all at once. This perspective revealed dynamic variations, such as shifting dust storms and nighttime cooling cycles. It showed that Webb isn't just a tool for studying the deep universe. It is versatile enough to contribute to planetary science close to home, complementing missions like rovers and orbiters. Even our nearest neighbors appear fresh and unfamiliar through Webb's eyes. Its discoveries are helping explain how galaxies like the Milky Way came to be. One of Webb's greatest contributions lies in connecting the distant past of the universe with our own galactic home. By observing galaxies at different stages of development, Webb provides snapshots across billions of years. These snapshots act like a cosmic family album, showing how small protogalaxies collided, merged, and evolved into larger systems. The Milky Way is a spiral galaxy rich in stardust and complex structure. Webb's discoveries of early spirals, star clusters, and cosmic filaments help astronomers trace the exact processes that eventually produced galaxies like ours. For the first time, scientists can directly observe the precursors of the Milky Way, watching history unfold billions of years before Earth existed. Webb is, in essence, providing our galaxy's origin story, one written across like years of space and billions of years of time. Webb captured dust blown into space by dying stars. Stars nearing the end of their lives shed enormous amounts of material into space, enriching the cosmos with elements like carbon, oxygen, and iron. Webb has imaged this process in unprecedented detail, showing streams and clouds of dust expanding outward from red giant stars and supernova remnants. These dusty outflows are crucial because they eventually become the raw ingredients for planets and even life. By studying how much dust is created and how it spreads, Webb helps astronomers understand the cosmic recycling program that turned stellar death into new beginnings. Its infrared sensitivity is particularly suited to this work, as dust glows faintly in the infrared, invisible to optical telescopes like Hubble. With Webb, scientists can follow the journey of stardust from its violent birth to its role in building future worlds, a reminder that everything, including us, was once forged in dying stars. Its mirror alignment is so precise, it is like hitting a target smaller than a volcano. Webb's segmented mirror must act as a single, flawless surface. To achieve this, engineers aligned each of its 18 hexagonal segments with a precision of nanometers, billionths of a meter. The final accuracy is often compared to hitting a target smaller than a virus. This alignment is not a one-time event. Webb continually adjusts its mirrors in space to maintain perfect focus. Achieving this feat required decades of technological development, including actuators capable of movements smaller than the width of a hydrogen atom. Without this extraordinary alignment, Webb would not be able to capture the sharp images that are now reshaping astronomy. It stands as one of the most delicate engineering triumphs in human history, a machine whose perfection rests on movements so small they defy ordinary comprehension. Webb revealed galaxies so faint they vanished in Hubble's vision. Hubble, despite its legendary achievements, has a limit to what it can see. Some galaxies are so distant and faint that they barely registered or disappeared entirely in its images. Webb has brought them back into view. In its first deep fields, Webb revealed countless new galaxies that had previously been invisible, some among the earliest ever to form. These faint galaxies are essential for understanding the universe's history, since they likely played a major role in the Ryanization era that ended the cosmic dark ages. Webb doesn't just extend Hubble's reach, it opens an entirely new layer of the cosmos. Each faint speck of light represents billions of stars, all galaxies that lived, merged, and evolved long before our solar system came into existence. It has already spotted stars forming the same way they did billions of years ago. One of Webb's revelations is the continuity of star formation across cosmic history. By peering into both nearby stellar nurseries and extremely distant galaxies, Webb has shown that stars form through remarkably similar processes. Dense clouds of gas collapse, ignite nuclear fusion, and give birth to clusters of young suns. This similarity suggests that the physics of star formation has remained consistent for billions of years, from the earliest galaxies to our own Milky Way. What's different, however, is the scale. In the early universe, stars often formed in far greater numbers and at faster rates, shaping young galaxies into brilliant beacons. Webb's ability to witness these processes across time provides a unifying picture of how stars, and by extension, planets and life, have always come into being. Webb's spectrograph can observe 100 objects at once, Unlike many earlier telescopes that study one object at a time, Webb carries a powerful instrument called the Near-Infrared Spectrograph, NEOSPEC. This device can collect spectra from up to 100 galaxies, stars, or planets simultaneously. Each spectrum is a treasure trove of data, revealing the chemical composition, temperature, and motion of the target. This efficiency allows Webb to conduct massive surveys, building statistical samples instead of focusing only on individual objects. With NIRSpec, astronomers can map the large-scale structure of the universe more quickly and thoroughly than ever before. It turns Webb into not just a telescope, but a factory of cosmic insights, capable of producing data at a rate that accelerates discovery far beyond what past observatories could achieve. The telescope's golden mirror is more than 6 times the size of Hubble's. Hubble's mirror, at 2.4 meters across, revolutionized astronomy. Webb's mirror, however, is a giant spanning 6.5 meters, more than 6 times Hubble's collecting area. This size difference is not just about scale, it directly translates to sensitivity. A larger mirror gathers more light, enabling Webb to detect fainter objects and resolve finer details. The mirror's size is what allows Webb to peer back into the earliest epochs of the universe and to study the atmospheres of small dim exoplanets. Its hexagonal design, folding for launch and unfolding in space, represents one of the greatest feats of aerospace engineering ever attempted. Without this massive mirror, Webb would be blind to the faint whispers of ancient galaxies and distant worlds that now fill its images. Webb may one day provide strong clues about life beyond Earth. While Webb is not equipped to directly detect life, it is laying the groundwork for perhaps the most profound discovery humanity could ever make. By studying exoplanet atmospheres, Webb is capable of detecting potential biosignature gases such as oxygen, methane, and water vapor. In the right combinations, these gases, if found together, could hint at biological processes. Already, Webb has demonstrated its ability to characterize alien skies with exquisite detail, making it the most powerful tool yet in the search for habitable worlds. Within the coming years, it may identify planets with atmospheres that look strikingly Earth-like, raising tantalizing questions about whether life has arisen elsewhere. Webb is bringing us closer than ever to answering one of humanity's oldest questions. Are we alone in the universe? It revealed the hidden skeleton of the cosmic web in stunning clarity. The universe is not evenly filled with matter. Instead, galaxies trace vast filaments of gas and dark matter that stretch across cosmic space, forming what astronomers call the cosmic web. Webb has imaged parts of this structure in unprecedented detail, showing how galaxies cluster along these filaments, like dewdrops on a spider's web. This hidden framework is thought to have guided the growth of every galaxy, including the Milky Way. By mapping these cosmic highways, Webb provides crucial insights into how gravity shaped the universe on its grandest scales. These observations are not only visually breathtaking, but also scientifically vital, connecting the smallest scales of star formation to the largest structures in existence. Webb is revealing the very bones of the cosmos. Webb captured light from stars that lived and died billions of years ago, is not only a telescope, but also a time machine. Because light takes time to travel, Webb's images capture the glow of stars that no longer exist. Some of the photons it detects began their journey more than 12 billion years ago, long before our solar system was born. These stars lived fast and didn't die, seeding the cosmos with heavy elements that would one day form new stars, planets, and eventually life. By studying this ancient light, Webb allows astronomers to reconstruct the life cycle of stars in the earliest galaxies. It is astonishing to realize that, as you look at Webb's images, you are seeing stars that blazed and faded before Earth even existed. Ghostly beacons preserved in their final act across the abyss of time. Its data showed galaxies forming far faster than expected. One of Webb's most surprising findings has been the discovery of galaxies that formed at breakneck speed. Astronomers expected early galaxies to be small, faint, and slowly growing. Instead, Webb has found massive, bright galaxies appearing just a few 100 million years after the Big Bang, much earlier and larger than models predicted. These discoveries suggest that star formation in the young universe was far more efficient than previously thought. It raises questions about whether we need to revise theories of dark matter, cosmic inflation, or the physics of starbirth. Webb is not just filling in details of the early cosmos, it is forcing scientists to rethink the fundamentals of how the universe evolved. Every observation is a reminder that the universe still holds mysteries that defy our expectations. Webb's mission proves humanity can build machines to touch time itself. From the moment Webb began returning data, its success became more than a scientific triumph. It became a human one. The telescope's ability to look back over 13 billion years into cosmic history shows that humanity can design tools stretch the limits of imagination. The thousands of years people have wondered about the beginning of everything. Webb is proof that we can now reach back and actually see it. Its mission demonstrates the astonishing blend of vision, patience, and engineering that humans are capable of when united by curiosity. Webb is, in a sense, a mirror not only of the cosmos, but of our own ingenuity, showing that we are able to build machines that quite literally touch time. Its images have become some of the most detailed ever taken of space. When Webb's first images were released in July 2022, they immediately redefined what astronomy looked like. The level of detail was breathtaking. Towering clouds of gas lit with newborn stars, galaxies stretching to the edge of time, and intricate structures in nebula glowing with eerie beauty. These images are not just beautiful, they are packed with data. Every pixel contains information about temperature, composition, and distance, making them scientific gold mines as well as works of art. Compared to Hubble, which itself transformed astronomy, Webb's pictures have 10 times the resolution in infrared. They are already considered among the most detailed cosmic portraits ever taken, the kind of images that will remain iconic for generations. Webb revealed unexpected brightness in galaxies from the early universe. In studying galaxies from the first few 100 million years after the Big Bang, astronomers expected faint, barely detectable smudges. Instead, Webb found galaxies shining far brighter than theory predicted. This unexpected brightness suggests that the early universe may have been far more active, with stars forming at extraordinary rates, or with populations of stars very different from those we know today. Some scientists even wonder if exotic objects, like unusually massive stars or early black holes, might be contributing to this glow. Whatever the explanation, Webb's findings are clear. The early universe was anything but quiet. It blazed with activity, rewriting our understanding of cosmic dawn. Its discoveries will shape astronomy for generations to come. Webb is not a short-term mission. The data it produces is so vast and rich that astronomers will be analyzing it for decades. Many of Hubble's greatest contributions came years after its launch, as scientists mined its archive for new insights. The same will be true of Webb, whose discoveries will ripple through astronomy for generations. Its ability to probe both the earliest galaxies and the atmospheres of exoplanets means it spans the entire spectrum of cosmic questions, from the origin of the universe to the search for life. Even long after Webb's instruments fall silent, the knowledge it provided will remain a foundation for everything we learn about the cosmos. Webb showed that the universe is stranger than we imagined. Science often advances by disproving our expectations, and Webb has done this repeatedly, from galaxies too massive, too early, to atmospheres richer and more complex than expected. Webb is revealing a cosmos filled with surprises. Each observation seems to raise new questions rather than provide final answers. This is the hallmark of Webb: science. The more we learn, the more mysterious the universe becomes. Webb has shown us that the universe is not only vast, but stranger and more dynamic than we dared to imagine. It reminds us that humility is essential when confronting the cosmos, because reality often outpaces even our boldest theories. Its golden mirror is coated in just 48 grams of gold in total. Webb's iconic golden mirror isn't solid gold, but coated with an ultra-thin layer, about 100 atoms thick, of pure gold. In total, only 48 grams of the metal were used, roughly the weight of a golf ball. Gold was chosen not for its beauty, but for its optical properties. It reflects infrared light extremely well, making it ideal for Webb's mission. This thin coating transforms the beryllium mirrors into extraordinarily efficient collectors of cosmic light. It is astonishing to realize that such a small amount of material, carefully applied, helps unlock the secrets of the universe. The golden glow has become a symbol of Webb's precision and elegance, proof that sometimes the smallest details enable the greatest achievements. Webb will guide the search for habitable worlds in the decades ahead. One of Webb's most exciting roles is in studying exoplanets, planets orbiting stars beyond our solar system. By analyzing their atmospheres, Webb can detect gases like water vapor, carbon dioxide, and methane, which are key to assessing habitability. This doesn't mean Webb will directly prove life exists elsewhere, but it will narrow the field dramatically, pointing telescopes toward the most promising targets. In the coming years, Webb may identify planets that resemble early Earth, with atmospheres rich in the chemistry of life. This work ensures that Webb will remain central, not just to cosmology, but to the search for our cosmic neighbors. It is laying the foundation for one of humanity's greatest quests, finding another habitable world. It reminds us that the universe is still full of secrets waiting to be seen. Perhaps the most profound fact about Webb is not any single discovery, but the sense of wonder it inspires. Every image and data set is a reminder that the universe is far larger, older, and stranger than our minds can easily grasp. For all we know, Webb's greatest revelations may still lie ahead. The telescope stands as proof that exploration is never finished. No matter how much we uncover, there will always be new mysteries waiting, hidden just beyond our current reach. Webb reminds us that the night sky is not a finished story, but a living, unfolding epic, one we are only beginning to read. And so we drift gently to the end of our journey through 100 fascinating facts about the James Webb Space Telescope. Think of everything we have touched tonight. Galaxies too old to exist, stars wrapped in cocoons of dust, and worlds light years away with whispers of water and carbon dioxide in their skies. Webb has shown us storms raging on planets we can never visit, the faint glow of stars that died billions of years ago, and galaxies forming at impossible speeds at the edge of space itself. It is hard to believe that a machine built by human hands, delicate gold mirrors, instruments chilled almost to absolute zero, a sun shield unfolding like origami, can see so far, so clearly into the deep past of the universe. And yet, Webb floats quietly in the darkness, 1.5 million kilometers from Earth, gathering light that began its journey long before our planet was even born. As you drift towards sleep, imagine that golden mirror hanging in the blackness, reflecting the light of galaxies that no longer exist, of stars whose dust still drifts through space, waiting to form new worlds. Each photon Webb captures has traveled for eons, and when it finally reaches the telescope, it is as if the universe itself is whispering its history into our ears. These discoveries are not finished. In truth, they are only beginning. Webb will go on watching, recording, and revealing for decades, its images reshaping our understanding of the cosmos again and again. Perhaps it will show us the first black holes. Perhaps it will find the chemical fingerprints of life on a distant planet. Or perhaps it will uncover mysteries we cannot yet imagine. For now, though, you can let go of questions and simply rest. The universe is still out there, vast and shimmering, and Webb is keeping watch. You can close your eyes knowing that humanity has built a window into time, and through it we are beginning to see our place in the great story of the cosmos. Thank you for joining me on this journey tonight. May your dreams carry you safely among the stars, and may you wake with the quiet wonder that the universe is always larger, older, and more beautiful than we know.